So I just wanted to start off this video by saying thank you to Mr. Issa Waslas of Salamat School, but this is Ms. Fatima Abbas of Umar Fadl School here in Yahar. This is for grade 8 science revision. Just wanted to make some very important notes. The science exam will be 20 questions, 15 multiple choice questions, and 5 writing questions. Okay. So we will start off by practicing with these multiple choice questions. The first outcome we will look at says to identify the magnetic domains in different types of materials. Compare between temporary and permanent magnets. So let's start off by defining magnetic domains. A magnetic domain is a region in a magnetic material in which the magnetic fields of the atoms all point in the same direction. The important thing to understand about magnetic domains are they are grouped together. So this is where our atoms are going to be grouped together. Looking at this plastic cone, we know that plastic is non-magnetic material, but the reason why is because it does not have magnetic domains. So plastic is not grouped into these magnetic domains. The magnetic field of atoms point in many different directions. So if we look at the magnetic field of these atoms here, we can see north is pointing in this direction in this atom, but in this atom it's pointing in a different direction, and here this one is pointing in that direction, and this one is pointing in yet another direction. So this random pointing of the magnetic fields causes the magnetic fields to cancel each other out, making it a non-magnetic material. Non-magnetic materials can never become or turn into magnets or have magnetic properties. When we look at magnetic materials such as hadid, iron, or steel, steel is a mixture of made with iron. This magnetic material will be grouped into magnetic domains. So here's a group. This group is a magnetic domain. Here is another magnetic domain. So all the atoms in this group are pointing in the same direction, but the magnetic domains themselves are pointing in different directions. So again, we can see these groups have north pointing in many different directions. So what does that mean? That means, just like in our non-magnetic material, that these domains are going to cancel each other out, meaning that it's not a permanent magnet here. Steel nail is only a magnetic material. It is not a magnet. Magnetic materials can become magnets when magnetic fields of the magnetic domains line up in the same direction, and we will see that on the next slide. When we look at a permanent magnet, such as this bar magnet, we can notice that the domains are all pointing in the same direction. So all of these domains are pointing in the same direction. This is why it's called a permanent magnet. Now let's look at the difference between a temporary magnet and a permanent magnet. The magnetic field around the bar magnet will apply a force. So this bar magnet is applying a magnetic force to the steel nail. This forces all of the domains to point in the same direction. As these domains point in the same direction, the steel nail becomes a temporary magnet. The word temporary in Arabic is muwakkad. So it is a magnet for a short while. Think about how we made the chain of paper clips. We wanted to see how many paper clips we could get to make a chain from the magnet. As you attached the paper clip to the magnet, it became a magnet itself, and we could pick up more and more paper clips. These paper clips were temporary magnets. We did the same thing with this steel nail. We rubbed the steel nail onto the magnet 20 times. Once we did that, we could pick up paper clips. This was a temporary magnet. We could knock the magnetism out of the steel nail by throwing it really hard on the table several times. Then it would not pick up those paper clips. So temporary means muwakkad. It's only a magnet for a short time. Whereas the bar magnet remains a magnet all of the time. Some magnetic material can be made into a permanent magnet by placing them in a very strong magnetic field. And we even found that with some of the nails in class. So let's look at the first question. Why will a plastic spoon never act like a magnet? So we know that a magnet needs to have magnetic domains, and those domains need to be in alignment. So we look at the first choice here. Do plastic material have magnetic domains? The answer there is no. Plastic does not have magnetic domains. Is plastic a magnetic material? If it does not have magnetic domains, then it cannot be a magnetic material. It does not have atoms grouped into magnetic domains. So we can look back and see that this is true. It does not have atoms grouped into magnetic domains. But let's take a look at this last choice. The magnetic fields of the plastic spoon are lined up. No, they are not lined up. They have a random arrangement. So that means C is true. Now let's look at our next question here. Which model, A, B, or C, explains why a plastic spoon will never act like a magnet? We can see here that we have magnetic domains all facing in the same direction. So we're going to go ahead and type in that this is a permanent magnet. Here, B, it has magnetic domains, but they are all facing in different directions. So we're going to call this a magnetic material. Now looking at C, C does not have any magnetic domains with a random arrangement, so this is a non-magnetic material. So let's stop and think. Look back at the question. Which model explains why will a plastic spoon never act like a magnet? Plastic spoon never act like a magnet means that plastic is a non-magnetic material, making the best answer choice for this question the letter C. Now, again, before we even read the question or look at our choices, let's identify these materials. We can see here that we have magnetic domains all pointing in the same direction. So magnetic domains, they're grouped together. 2, pointing in the same direction. So we know that this has to be more than likely a permanent magnet. Here we have no magnetic domains, and each one is facing in a random direction. So they are canceling each other out. No magnetic domains, that means this is a non-magnetic material. So let's look at our choices. 1 is a non-magnetic material, while 2 is a permanent magnet. So let's look. That's not what we wrote. So A is wrong. Material 1 is a permanent magnet. Yes, that is true. Material 2 is a non-magnetic material. That is true, based on what we wrote. So we're going to hold off before choosing and look at the other things. Material 1 and 2 can be made using an electrical magnetizer. No, because non-magnetic material could never be a magnet. Material 1 and 2 are magnetic materials. No, 2 is not a magnetic material. So that leaves B as the only correct choice. Let's go down. Sada has made an experiment to investigate the material of 2 different paper clips using a bar magnet. And as seen in the figure below, paper clip 1 is attracted to the bar magnet, while 2 did not. What can you conclude? So we know that magnets can attract magnetic materials such as steel or other magnets, but will not attract non-magnetic material such as plastic. So paperclip 1 is made from steel. That is possible. While 2 is made of plastic. That is possible. Paperclip 2 is made of steel. That's not possible, because then it will be attracted to the magnet, while 1 is made of plastic. That's false, because it would not be attracted to the magnet. Here, paperclip 1 is made of steel. This is true. While 2 is a magnet itself. That is false, because they would be attracted to the magnet, or at least put force on each other. Paperclip 1 and 2 are made of plastic. That's not true. So the only correct answer, the best correct answer, would be A. Let's go to the next outcome, which says, explain how electric charges interact and list the factors that electric field strength depends on. So there are 2 types of electric charges. Electric charges, remember, work very similarly to, or electric force is very similar to magnetic force, because they're both non-contact forces. There are 2 types of electric charge. We have a positive charge and a negative charge. We know, just like magnets, that oppositely charged particles will attract each other. So positive will attract or move towards the negative, and similars will repel. So these will push away from each other. The invisible region around a charged particle is called an electric field. So each of these particles will have an area around it where force is applied, and this is called the electric field. So the electric field is the area around the charge that is going to pull or push the force, and this is a non-contact force because they do not need to touch in order to push and pull. Let's look at this question here. Why is this woman's hair standing up? So, in the photo, positive charge accumulates on the woman. The charges spread out and push away from each other. So this is one hair with a positive charge. This is another hair with a positive charge. What will they do? they will repel each other, because we know like charges will repel. So these two charges are pushing away. And no matter how many hairs we add up here, if they all have the same charge, they will push away from each other. Right? Okay, moving forward to the next. Factors that affect electric field strength. There are two factors we are primarily looking at. That would be the positive, the distance, the distance. So as these charges move further and further away from each other, as distance increase, the strength of the electric charge will decrease. And the inverse. So distance has an inverse relationship. As distance increases, strength will decrease. That's why these are getting weak as they move away from each other. Whereas charge has a directly proportional relationship. As the size of the charge increases, the strength of the electric field will also increase. So we can see the charge here is stronger. So the strength of the electric field is also going to be stronger. Okay, before, again, even reading the questions, let's go ahead and put these in categories. This here, we know, is oppositely charged because it attracts. Here, we know this is a neutral charge, because neither it is not attracted or repelling. And then this last one, we know this is similar charges. The reason is because we have repulsion or repels. So now, let's look at our choices. Our question first. It says, which balloons have an opposite charge? So we want opposite charge, and we already said one has an opposite charge. And move this over here. So we said one has an opposite charge. So that eliminates choice option B. So that eliminates B, and it eliminates D. So in pair figure 1, we know that they have opposite charges because they attract. If they repel, then they would be the same. So that eliminates choice C, leaving only A. Okay? Let's move on to the next question. While doing laundry, Jamal pulls clothes from the dryer. Some socks cling. What does this word cling mean? I wonder. To a blanket. Which statement explains why the sock clings to a blanket? Let's look at the picture now. What are the socks and the blanket doing? Oh, I know what cling must mean. Cling must have something to do with attraction. So let's rewrite the question a little bit. Socks are attracted to the blanket. So let's now take a minute to think and process. What do we know about attraction? We know that opposites attract. So let's skim and scan and see where we see something about opposite. Here. We can see the clothes picked up opposite charges, so that's true. Opposite charges are attracted. That is also true. Let's just go back and make sure that our choice is correct. The socks and blanket dry together, which causes them to cling. Even that's not quite a cause and effect relationship. The socks and the blanket are conductors that picked up some positive charges. Maybe they have some conductive properties, but no, and it doesn't say anything about the negative charges. We would need positive and negative charges to have attraction. The socks and blankets are insulators that picked up some negative charges. Yeah, they're more than likely insulators, but again, we would need positive and negative charges to have the attraction, because attraction happens between oppositely charged particles. Okay, so this outcome will be the last outcome for this video, where we will look at electric circuits. Here it tells us to illustrate how electric particles flow. So here's another word that we should know, which is flow, and differentiate or tell the difference between closed circuits and open circuits, and list the factors that affect electric current. So like I said, a word we should know here is flow. So the word flow means movement. Is to move. So water flows down the river, so it's moving down the river. Electric current is the flow of electrically charged particles. So here, a current is going to be the movement or flow, again, of those charged particles. So those charged particles are moving from one place to another. And we know that that can happen if we have a conductor. An electric circuit is a closed path. So the easiest way to think of a circuit is that a circuit is going to be a loop. So a closed path where the electric current can flow to and from a source of energy. So a circuit is going to be any kind of closed path. So when we talk about car racing, cars race on a circuit or a closed path. I think I made this picture not so nice. Okay. So let's look at this closed path of electricity. All simple circuits contain three main things. A source of electric energy. So here's our source of electric energy. That's the battery. They contain a device. It's changing colors. Here's our device. And then they contain conductors. And our conductors would be these wires that allow for the flow or the electric current to pass from the battery to the light bulb. Okay? Circuits will also include a switch. A switch is used to open and close the circuit. So what do we mean by open and closing the circuit? A circuit is open if there is a break between the conductors, because that doesn't allow for electricity to flow in the circuit. So we have this opening here between this conductor or this switch, and that is why we would call this an open circuit. So the light will be off. A closed circuit allows for that continual flow of electricity from one end of the battery to the other end of the battery. And therefore, it is a closed circuit. How can what is a factor? So remember, we need to list the factors that affect an electric current. One factor that's going to affect this current is whether it's on an open or closed circuit, because the current cannot flow if the circuit is open. Another factor that will affect this battery is this circuit is how much energy is flowing through the circuit. We can see here that we have a 3-volt battery. So when we did created circuits in class, we were using a 1.5 volt battery. And then we got a dim light. By increasing the voltage, adding more and more batteries, our light was able to shine brighter. That brightness was due to increasing that voltage here. So when you went from 3 volts to 6 volts, in this case of the pictures, we can see that the light shines brighter. So this is a simple, straight definition question. What is an electric current? Remember, the word current, just like the current of a river, will be a flow of electrically charged particles. It is not a force. And it definitely moves. Electricity is a type of kinetic energy, and we all remember Takaharakia. Next question is telling us a 1.5 battery is connected to a light bulb. I'm going to circle this. It's giving us information. With some wires. One of the wires is cut, breaking the circuit. Okay, so we see that the wire is cut here. What is the electric potential energy difference across the light bulb? So we're comparing the energy that is flowing here from the positive end to the electricity flowing here. Since we are only measuring the energy from one side of the battery, we know that that will be 0, because that is only the positive end of the battery. Let's change colors here and look now at this. After the wire is cut, the electrical potential energy difference across the 2 ends of the wire. So now we have 2 ends of the wire, both connected to different ends of the battery, which means we can now measure the potential energy difference of this battery, which we know is 1.5 volts, and we know this because of the reading here. So when we are measuring from the ends of the wires, we are measuring from, those are just acting as extensions of the battery. Okay, so I'm going to stop this video here, because when we start talking about electromagnets, it is useful to watch the video. So I will see you in part 2 of this video. Masalama, have a great